Hello, Chem 19 students. This is Professor May Joan Aguila, and this video lecture is about redox properties, particularly the segment about the Frost diagram. So, Frost diagram is also sometimes referred to as the oxidation state diagram. So, in this diagram, we're plotting the relative free energy of the species versus its oxidation state. So basically, it is the plot of N standard potential versus N, which is the oxidation number. So this is the usual representation of the Frost diagram. So you can see here in the y-axis, it is sometimes written as negative delta G over F. And you can see here, this is a Z multiplied by the standard potential. Z here is the number of electrons. But we notice, of course, that Z and N are not exactly the same, except when the point of view here is from X0. So the form of the element in zero oxidation state. So from X0 to whatever the oxidation state or oxidation number N, the number of electrons that will be involved would be N. So this equation or this plot is the same as N E naught. So for Frost diagram, we can figure out which is the most or the strong oxidizing agent or strong reducing agent. And since this is a plot where it tells us, so from the delta G, it tells us the thermodynamic stability of the oxidation state, so the inherent stability of the oxidation state, we can infer what or which of the oxidation state and hence which form of that element is more stable or unstable. But please take note that this plot or this diagram does not tell us anything about the kinetics, only the thermodynamics. And usually, we can see that each point is connected with a line in this diagram, and that connectivity, of course, tells us the direct relationship of the neighboring species. But you can also connect non-adjacent species, and we can also infer some information about non-adjacent species as indicated. So the way that we will interpret or what information can we gather from the Frost diagram? First off, how are these diagrams essentially constructed? What does each point, what does this point means? What does this point mean? So I have it here, the Latimer diagram for the manganese containing species in the acidic solution. So that's one consideration in the Frost diagram. The conditions should be the same for all the species that is plotted in one diagram. So if it is in basic solution, you need to plot it in a different diagram. Although these are both manganese-containing species. So it is going to be from the point of view of the most reduced, or the elemental form, or the one which has a zero oxidation state for the element. So in this case, manganese 0. So from manganese 0 to here, what does this line mean? That line actually means the potential. But what potential are we referring to? It is always going to the form wherein it is zero oxidation state. So this this line over here is for the potential for the reaction Mn2 plus plus 2 electrons to give you Mn. So essentially the reduction. And from the Latimer, we found that that is negative 1.19. So this is negative 1.19. So from this illustration, we can see that essentially the potential is the slope of the two dots of the line that connects the two dots, or the two species of different oxidation state. So this point is at 0, 0. This point is at positive 2. But what about the y value? So how do we calculate the y value here? So what is this equivalent? Why isn't it not negative 1.19? Remember, the y axis is Ne, or the oxidation number, multiply with the potential. So this y value here should be negative 1.19 times 2. So that's around negative 2.38. Okay? So this point to this point, okay, this slope should be equivalent to 1.54. So should be equivalent to 1.54. But what is this value over here? So we can calculate that. So basically, this is the reaction that is exemplified by that one. So using the equation for non-adjacent species, so we have 1.54 times 1. So from this part, plus negative 1.19 times 2 from this part, divided by the total number of electrons. So this would be negative 0.28. So this potential is negative 0.28. But since the y-axis should be Ne naught, so oxidation number, this should be 3 times negative 0.28. So this is negative 0.84. So this value is at negative 0.84. Okay, so obviously it's going to be from the point of view of going to the most reduced form. So if it is this direction, so that means the potential going to the most reduced form, as we can see for manganese 2 plus to manganese, it is negative. Okay. Same as manganese, manganese 3 plus to manganese, it's also negative, negative 0.28. But we see over here manganese 2 plus to manganese 3 plus, so it is, so from manganese going to manganese 3 plus going to manganese 2 plus, as we can see over here, it's positive. So we have a positive slope like that. So obviously going from left to right, it is more oxidized form. Be aware though, in some Prost diagram, so listed here is what a normal number line is. So we have negative values here going to positive values, in between it 0. But in some representation, that is not the case. So just be mindful about that. For species that has negative oxidation state, for example, so totally unrelated to this Prost diagram anymore, so I just want to include it. So reduction, the reduction of bromine to Br minus has a value of negative delta G naught of positive 1.09 volts. So if we have this Prost diagram, so this is the 0, 0 mark, so that's where Br2 would be. So negative 1, so bromine, so this is bromine. Now let's just say this is 1.09, this is negative 1.09. So which position should I place the dot representing Br minus, A or B? In the Prost diagram, remember, it's always going to the most to the zero oxidation state. I cannot say most reduced form now because bromine minus is essentially, the bromide is the more reduced form of Br2 minus. So it's going to be to the zero oxidation state. So in this equation that we have over here, it is actually the opposite one. It's going from 0 to negative 1. We wanted the other way around. One thing that you can always remember is this is an oxidation diagram. So we're representing it as oxidation. So we have Br minus 2 1/2 Br2 plus E, and E naught here is equivalent to, this is Ne naught pala. Ne naught is equivalent to negative 1.09 volts. Okay, so negative um, 1.09 volts. So essentially, we just reverse the sign of E naught because we reverse the direction. Instead of reduction, it becomes oxidation. So we will use B as the plot for Br minus. So this would be the segment in the cross diagram representing Br minus to Br2. So aside from the usual calculation of E, so we check it here from the slope. Of course, we can relate this to delta G naught based on the equation that we mentioned in the in the electrochemical potential video. Some other informations and more qualitative that we can gather here. Since when we go down the figure, remember this is delta G and this is thermodynamic. We're telling about the thermodynamic stability of the charges. So as we go down, we have increase in thermodynamic stability. And the species at the bottom would be the one which is the most stable oxidation state. So the form which has the most stable oxidation state for that element. So in this case, it's going to be manganese. And then, looking again into the plot, since this region, top right, is highly oxidizing region, whichever species is at the top right means it is a very strong oxidizing agent. So in this case, that would be manganese, permanganate ion. Also, by looking at the figure, we can predict if the species will undergo disproportionation. Again, disproportionation. So only one compound or one species will undergo reduction and oxidation at the same time. Okay. And what we need to check here is the portion where it appears to be there's a convex region. So convex okay, so this is the red ox, this is ox, this is red. So this is the convex region. If the 3 points make a convex region, that means this species that we indicated here as red ox will undergo disproportionation, or it is not stable, it is unstable against disproportionation. And in the plot, there are 2 species that actually have that, HMNO4 minus and MN3 plus. You can check in the Latimer diagram if indeed this is true. Remember, in the Latimer diagram, we check if the potential right versus left, if it is greater, so it will undergo disproportionation. Aside from this, we can also qualitatively figure out which undergoes comproportionation. So COM and then proportionation, same as the proportionation in the disproportionation. So this is the opposite of the disproportionation. So the species when it get reduced and when there's an oxidation, it will only result to only one species. Okay. So the net product is only one. So there's no separate oxidized form and there's no separate reduced form in the product. In this case, we're going to take a look into the concave part of the plot or the diagram. So this is the illustration of the concave plot of the diagram. So this means that the oxidized form has the natural tendency to go to the redox form. At the same time, the red form will go to redox form. And that's what we meant by comproportionation. And essentially, in this plot, that's MnO2. So MnO2 is the product of comproportionation of HMnO4 minus and Mn3 plus. So take note, HMnO4 minus and Mn3 plus are the ones that undergo comproportionation to give MnO2. On the other hand, HMnO4 minus undergoes disproportionation to produce MnO4 minus and MnO2. Alright, so with that, we have the information that we can gather from the frost diagram.